the stage is yours, and here's Adam with back action in the circular motion Unruh Effect.
Thank you very much. How is this? Is that too close? Is the mic going to be a problem there? If there is, then chat will let us know. Yeah, we're talking about the back action in the Unruh Effect. So it's kind of a weird talk to go first, because most of the talks will talk about the Unruh Effect and how the detector changes, how the detector transitions. It's a very traditional way of looking at the Unruh detector field interaction. But instead of that, I'm going to be looking at the, I think, just as interesting counterpoint to that, to what happens to the field after it interacts with a detector. And I think there are equally interesting quantum relativistic nuggets to be found deep within that question. So I'm going to start off by just quantifying that field state. I'm going to quantify that thing that you get in the field after the interaction instead of what you get in the detector. Then I'm going to specialize down to 2 + 1 dimensional circular motion, a kind of motion that you'll be very familiar with by the end of today. And then I'm going to show you some plots, and that will be the good bit. So stick around for that. So to start off, let's define the things we're working with. We have a detector. We have the Unruh-DeWitt detector, a 2-level system with an initial state, which is defined here as 0, and a secondary state, E. I will try my best to not call it an excited state. If I do, I'm messing up, because it's not necessarily excited. The gap between the initial and secondary states can be positive or negative. There can be excitation and there can be de-excitation. And they're both interesting questions. And then they interact with this Hamiltonian in a very traditional way. There is plenty of literature on this, Unruh's 1976 paper being a very good example, which is where he first mentioned it. Was that the first time? I'm actually not sure of that. But we have a constant using perturbation theory, this lambda that I will try and point at with a laser that I don't point in my eyes. There we are. This lambda here is a constant we need for perturbation theory. There is also a chi, which is a switching function that I'll talk a bit more about later on, which defines how we turn the interaction on, how we turn it off. The detector monopole moment operator sits in here, which gives the detector a degree of freedom to transition up or down, however it sees fit, and be coupled to the field. And this is specifically the field along this x of tau, this proper time of the detector, along the path of the detector, parameterized by its proper time. Once we have the interaction Hamiltonian, and we have our perturbation theory constant, we expand in time-dependent perturbation theory. For that, we need a Dyson series, and I'm going to go a bit further back than most things do. I'm going to try and explain how we get to this field state. So we evolve it with a time evolution operator. We set our initial conditions to be at -infinity, and we're going to evolve to some future time. And we set our upper limit here to infinity because we're looking after the interaction. Because we're after the interaction, that upper limit doesn't matter. Our Hamiltonian is 0 as long as we're after the interaction. So this upper limit can be anything we want. We can just kick it all the way up to infinity, and the maths becomes possible. Difficult, possible. So from here, our initial conditions that we set, we have the initial state of the detector and a vacuum in the field. And then we act on it with the Hamiltonian. We substitute the Hamiltonian in here, and we get a little bit of a mess. Not a bad mess, a little bit of a mess. This thing here is kind of messy. This is a one-particle superposition in the field modes. And that is the thing that is emitted that we're trying to look for when the two things interact and the detector transitions. For this talk, I'm just going to call it V. I'm going to completely ignore it because explaining the details of those numerics is a pain that I will not share with you. And there are 2 states here which result from the 2 possibilities to lowest order in perturbation theory in the field state. Either nothing can happen or something can happen. Nothing can happen, or we get a transition to the secondary state, and in that transition, the field changes states to this V, this emitted other field mode, which is a bunch of one-particle states. From that, to say anything about the field, we need to find observables in the field. We need to choose an observable. We need to look at that observable. And you actually find, if you plug in, the mouse is in the way, if you plug in, find the expectation value of any field observable A, and it's just a tensor product with the identity for the detector, because we aren't observing that yet. Well, we get the vacuum expectation value of the observable A, and we also get this field state V. So basically, to leading order in perturbation theory, as far as we know yet, we have a vacuum contribution that we will set to 0 because it's constant everywhere, and we have this perturbed thing that we're going to actually look at and that I will try and plot and find. And for the sake of this talk, I'm going to keep it simple again, because the numerics, as I think I've hinted at one too many times, are a pain. So I'm going to look at phi squared, a very simple case, the amplitude of the field. Future possibilities could expand to look at the stress energy tensor, T00, the energy density, particle number density, everything's accessible from here. It's a matter of what to choose and what is most relevant for literature, what you can find the most information from. And also what you can calculate. And with that, we need to specialize down and talk about specifically what am I working with. I'm working with, as I said earlier, 2 + 1 dimensional circular motion. There is a detector, it goes in a circle through time, it spirals and spirals forever. I think this is a very interesting geometry and trajectory to look at for a few reasons. First of all, the circular equivalent of the Unruh effect is not something that's as well understood. It's not something which is as well behaved and as clean. There is this notion of a Bugli-Above transformation, which is how you can derive the Unruh effect in full in the linear case. That whole notion is unambiguous in the circular case, which means that directly finding anything in the traditional way is much more difficult. The other reason, and I'm not sure if I should have put this on here because this isn't something that we've actually worked out yet, but there is the potential for an analogy to experiments that are going on in Nottingham that you'll hear about later on, potentially measuring certain field observables through that, which would be also interesting because analog gravity is fun, as I hope you'll agree with me later on. Finally, the last little wrinkle that I need to talk through before we get to something more interesting and more fun, which is obviously graphs, is the switching. How are we going to define the switching? Because as I mentioned earlier, our formulas are only valid after the interaction has stopped happening. And to get to that point, we need to find some switching which switches off, and then we look at it at the point where it switches off. But to extract the most information from the interaction, to get the most excitations out of the field, you also want a very long interaction time. So what we use for these plots is what we call a half-infinite interaction, where before 0, before some time, it is, and for all time before that time, we have 1, and then we have a gradual switch off over a certain duration that we can control, ideally a fairly fast one, so we can really look at the interaction, and then it's 0 after that point, which means that we can look at the field exactly here, where the interaction is 0, and any time after that, and we can evolve through and see how the interaction evolves. Enough of the boring stuff. So we get spirals. So this is a space-like slice of the field, specifically of phi squared of the field, at a particular time. And this is specifically at the time when the interaction is 0, the first time that we can ask this question. And we get these spirals that have been plaguing me for far too long. The shape of these spirals is actually very predictable analytically. If you imagine the detector was holding a laser beam and it ran in a circle, the plot that laser beam would put, the tangent null vectors along the path of the detector would plot out this exact spiral shape here. what we've got here is, to keep explaining things, there is a velocity of 0.5 c on the detector, and the detector switches off over the course of one cycle. So from, I think it starts here, and the detector ends there. We have one rotation for the switch off time of the detector. And of course these plots move, because that's much more fun. And what we see here is interesting different interactions for different energy gaps. Positive and negative energy gaps give this interesting different behavior, and around the energy gap 0 you see this much more spread out response. And I was very proud of this. I was thrilled, and I sent it to Bill Unruh to look through. And he wasn't as thrilled as I was. So I got an email that I won't bore you with right now, but the main thing is the sentence, "This answer means nothing." I wasn't thrilled about this. I haven't wasted your time, because I think there is genuine, interesting information in what I've shown you. But this was a bad day for me. So what did he mean? Well, back here, remember, if your attention span is long enough, you might remember these equations for the field state and any observable that we're trying to measure. The issue was I hadn't gone far enough. If you expand this lambda squared term in the state, and I'll explain why that you do that later on, then you get this initial state of the detector and a two-particle state in the field. And what happens is, you do the same maths, you find an observable, and to leading order in any observable you try and calculate, you get this correction here. This non-zero term coming from that two-particle state. And what this corresponds to is the detector transitioning twice, is where you get this from. So you get two particles emitted, one from a detector going up, I guess, or down, one from the detector transitioning to the secondary state, and one from the detector transitioning back to its initial state. So there are two distinct things happening here, technically three, because nothing is also a thing that can happen, and what you get is a superposition of these three possibilities. And then, after modifying our equations in the way that Bill told me to, I get much more interesting graphs, I think. There's a lot happening here. So first of all, you'll notice we now have negative values on all of these graphs. Before, everything was positive, and that's something which is predicted in some of Bill's older work. He had a 1986 paper where he talked about emissions always being positive, the stress energy tensor. The stress energy tensor is always positive if you don't do this correction, which is what I saw. And that's an issue. That can lead to infinite energy being extracted from the system through some mechanisms. This correction is much happier. And what you're seeing here is a negative energy contribution from that two-particle state. From that, sorry. It's not energy here explicitly, but this same thing holds for T00 as well. And you see this negative emission coming from that double emission. And that double emission is more likely for excitations. And the reason for that is that after the detector has, if the detector has transitioned to a secondary state, and that state required an upwards transition, it is then unstable. It then wants to go back down again. So if you have excitations, you're much more likely to get this double transition, which is where you're much more likely to see this negative bit. The other thing that's interesting on here is this little trail here that you see only at E bar is 1.1. That trail is the energy impulse from the switching itself. The switch off happens over one rotation, as I mentioned earlier, and the field contribution that comes from that switching is evident here. It exists here, but it's much less noticeable. At this E bar is 1.1 with this negative field emission, there is a really strong upwards kick that happens just from the switching. And that is less prominent on most of the other graphs. And there's plenty here. I could talk about these for hours, but I won't bore you. But I will animate them, because that's just more fun. Yeah, Silke?
So, why is it just repeating the video, or why is it
Yes, it's repeating the video. So this is from pi to 5 pi, which is pi is where the interaction has just finished, and then 5 pi is just an arbitrary stopping point where it was.
What is surprising, perhaps to me, is basically if you had a finite size system, the waves would come back at you. You'd get, these are. So what are we looking at?
This is infinite. This is not finite size.
But is it?
This is Minkowski.
Excitations you inject into your quantum field, and this. How big are these excitations? Can I think?
What do you mean, how big are they? We're working in perturbation theory, so these are just perturbations that are of an...
Have an amplitude, no?
This is the field amplitude, but up to an order of perturbation theory. So we aren't... So the exact height of these is only relative to each other. It's not as relevant on its own.
So if I interact with my quantum field, if a detector that interacts with the quantum field theory,
Mm-hmm.
if you increase, for example, in the coupling between the detector and your quantum field, are these perturbations larger? What sets? I mean, you say it's up to something, but can you make it an absolute value? Can you say what do you have to? We're talking about back reaction. How can you reduce back reaction? That's my question. So you have back reaction. What if I want to reduce it? What would I need to do?
It would depend on the observable you're trying to minimize. For the field amplitude here, for phi squared, you can minimize it by actually, for any of them, you can minimize it by optimizing the excitation gap of the detector, or the transition gap of the detector, between positive and negative, and large value and small values. But it would depend on the observable that you mean to which value of gap would minimize the back action. So here, this phi squared, the magnitude of it is minimized for just a large gap, means that it's less likely. T00, based on some earlier plots that I made that I have a level of confidence in, suggested that the higher the excitation gap, the less likely for T00.
Question more precise. Come on, cut me off in a second. So if you increase, but if this comes at the cost that you also minimize the Unruh effect, right? If there's, you say, well, once I don't see anything about detector, I also don't inject an excitation in my quantum field, then it just means you made the effects more. So my question would be, is there a way to maximize the Unruh effect? And I think the answer is no, but maximize the Unruh effect, what you measure on your detector, but reduce the back action.
The only other three parameters that I have here are the velocity and the duration of the switching. Both of them I can imagine having equal impact on the Unruh effect, but I can't know that for sure. There's a chance that there is an optimized switching, which where you still see Unruh effect, but you reduce the impulse of switching into the field, because, as I say, there is a emission from the switching itself. But I imagine, if you increase or change V, you'll increase or change the magnitude of this, but you'll do the same thing for the Unruh effect. So I can't think of any degree of freedom that I have that could let me do that.
I think that's a very interesting discussion to continue in the lunch break. So, Adam, if you'd like to continue.
Yeah, I'm pretty much done. I've also got them in 3D. Me and Jorma. That was an accident. I genuinely had forgotten. Me and Jorma continually argue as to which one's clearer, so I thought I'd include both just to be safe. If anyone gains any further insights from these, then please let me know at the lunch break, because I'm apparently low on time. For now, I'm just going to summarize. I'm asking what I think is the underrated but very important question of how does the field react to a detector as opposed to the other way around. There is a general procedure and there's a general derivation that I hope to use in future in a variety of situations. But for now, I just have these plots of 2+1 circular motion. If there is an excitation requirement, then you have this more of a negative field emission, which comes from this double transition. And for certain values of the energy gap, you get a larger impulse from the switching. So if you want to minimize that, you'd either need to have smoother switching, which would reduce how much you can see in the plots, or you'd need to pick energy gaps such that the switching has less of an influence. And finally, be careful when working in perturbation theory, and be doubly careful if you're emailing Bill Unruh about it. I have some references, and I'll accept any questions now. Thank you very much.